Welcome. This time I want to go through and introduce some concepts around irrotational flow, it's called. So this is flow which has, as we'll see, no vorticity or no local rotation. In the process, this will introduce some important concepts such as the static and dynamic pressure and different ways of rewriting the momentum equation, the concept of irrotational flows and some of the use it has in simplifying the equations, and then we'll start to introduce this concept of vorticity in fluids and what it means. We'll go into more detail on that in the next few talks. But for now, we'll just start by looking at what happens and different ways of writing the momentum equation. So in Euler's equation, we've already derived that we have du by dt plus u dot grad u, and then this is minus 1 over rho grad p. So p is the pressure, rho is the mass density, and u is the flow speed of the fluid. Now there are lots of different ways of writing this. We've seen different ways of writing the Euler equations. One that I want to introduce is to use a vector identity and just write this term here and write that as curl of u, which we'll see repeatedly. This is going to turn out to be vorticity. That's why this is such a useful thing to do. And then plus the gradient of a half u squared. So this is a vector identity, so we haven't made any assumptions in here. But what we can then do is we can try and group this gradient together with this pressure gradient here. And now in order to do that, we need to be able to move this density inside here. And so for now we're going to assume incompressible. So because we've started the Euler equations, it's an ideal fluid, so there's no viscosity or anything. So it's ideal and incompressible. And so this means that we see that divergence of u is equal to 0. It also means that density variations are small. So density, and this allows us to move density through the gradient into the pressure equation, into the pressure term here. So this density can now move through here. So this allows us to group this term, the gradient of u squared, with this term here. And so we can write down that we have du by dt plus this term here from the advection term. So plus, so this is coming just from here. Now we're going to move this term here onto the right hand side, and so it's just minus the gradient. Now I've moved the rho inside, so we have a p over rho, and then this term as a plus a half u squared. This is quite an important quantity. This is called h, so the head of pressure. Essentially this is a combination of a pressure kind of term and what looks a bit like kinetic energy. So if you multiply h by rho, this becomes a bit clearer. So this is pressure plus a half rho u squared. Now this term appears in many different places. This can be thought of as a total pressure. This is something called, this is the static pressure, and this is the dynamic pressure, sometimes called the ram pressure, but we'll just use static and dynamic. So essentially this is going to turn out to be constant in many cases. So if you have for example, a stationary steady state fluid, so for example this is steady state, in many cases we'll see that this u is a constant, and so along the flow, pressure is converted between the static pressure and dynamic pressure, but the total is constant. And we can show that in various ways. In particular, we can look at it in steady state. So we can say in steady state, in steady state, so d by dt is 0. So this first term goes to 0. what we do is we can take the dot product of this equation with u, so just u dot this. Now this term here is a cross product with u, so this is perpendicular to u. So u dot this is 0. And so the left hand side of this equation is entirely 0. And now here we have a u dot grad. There's a minus sign, but I've just moved that over and cancelled that out, so it doesn't matter. So we have a u dot grad h. So this is this p over rho and half u squared. And what this means is that this h is constant along the flow. It's constant. Historically, this was quite an important discovery in understanding aerodynamics, for example, and development of aerodynamics, because it allows you to essentially simplify cases where you, for example, have air flowing over wings. In many cases, you can then simplify and assume that this is constant along the flow direction. Okay, so the second interesting case is if we look again at this equation. So we've made this 0 by taking dot product with u, but we could make this 0 by making this curl of u 0. So if you make this 0, then again this whole left hand side goes to 0, and now we have the gradient of h is 0. So if second case is, so if curl of u equals 0, then gradient of h is equal to 0. And this means that h is constant not only along the flow but everywhere. So h is constant everywhere in our system. H must be a constant. And this case where we have curl of u is 0 is called, this is irrotational flow. And it provides a very useful approximation because it simplifies things enormously, and it turns out to be actually not too bad an approximation in many cases. See a little bit later on that when if you start with a flow which has this property, if you assume it's an ideal flow away from boundaries, for example, then this will continue to be true in many cases, and so this can be a useful and in some cases useful approximation. In particular, what it allows you to do is simplify the momentum equation, because we can write the flow velocity is basically gradient of a potential. This is a flow potential. And so this means we have three quantities. We have velocity in x, y, and z, and here we just have one. And so we seem to have lost some degrees of freedom. What's happened is, because we've imposed this imposes two constraints in terms of on the system, and so we've lost 2 degrees of freedom, and so we just end up with one quantity, the flow potential, which determines the entire flow field. And this means, of course, that the curl of the gradient is identically 0, so this will automatically be satisfied. And this allows us to simplify the equations. So we can put this back into the momentum equation. So we have d by dt of gradient of phi. Now we have a curl of u term which has gone away, and now we have a minus gradient of p over rho. This is this h quantity plus a half u squared. And so here we have a gradient and a time derivative, and they commute, so we can take the gradient outside. And we can integrate this whole thing in space. We just end up with a d phi by dt is equal to minus p over rho minus a half u squared. And then here we can add, in principle, we could add any function of time, because anything which is constant in space will be 0 when we differentiate it, when we take the gradient. And so this could be any arbitrary function of time, but it must be a constant in space. This turns out to actually not matter, because here phi, we only care about the gradients of phi. So the gradients of phi give us the velocity, but the actual value itself can be shifted up and down. We can add a constant to it and it doesn't make a difference, because when we calculate the velocity we take the gradient in here. And so this term we can just redefine phi and essentially choose to make this 0. And so we end up with an equation which is a non-steady state equation, so it has time derivatives. It tells us how the flow is responding to changes in say pressure and velocity. And this is Bernoulli. So Bernoulli's equation for unsteady flow. And this has been an interesting and useful equation in the development of aerodynamics, as I said, because it allows many other calculations to be made analytically. Okay, so the last case I want to discuss very briefly is what happens when this is not equal to 0. So what happens when curl of u is not 0? And this, so when curl of u is not equal to 0, so it's not irrotational. So this is the vorticity. So we have vorticity in the system, means the local rotation of the fluids. And next time I'll go into looking at how this evolves in time and how the vorticity behaves in the fluid. Thank you very much. See you next time.